Lead is one of the oldest materials used for lowering the melting point of silica. Silica's glass, that's what you put on pottery to melt to make it so it's waterproof and doesn't grow bacteria and doesn't leak and all that.
Oh, wow.
Yeah, so lead is extremely poisonous. What I find about lead, just coming from an art perspective, and especially ceramics, we use all kinds of minerals and metals and et cetera in the clay bodies and the glazes, and so and lead has been used traditionally for a couple thousand years. I think the Syrians and the Babylonians discovered, maybe the Chinese too, discovered lead. It's the most powerful melter for silica. Silica glass normally melts at 4,500 degrees, and this can bring it down to like even as low as 900 degrees or so. And it's interesting, we're doing this all over the place as humans. We dig things out of the ground, and then we put it in the air, or we put it back in the ground in the wrong way to where it's poisonous for us. This project it's not just art, it's also about healing, and also, the remediation. It's about making something that was poisonous and making it not poisonous, and there's different ways of doing that. You were talking about plants being able to do it, and there's some of the plants are being shown in the videos.
Yeah, there are organic chelating agents, inorganic chelating agents, and just as you said, what we've been doing with lead is taking it out of the soil in a state that's fairly inert biologically.
Yeah.
Right, and then converting it to a more active form where it really drives what we call oxidation reduction reactions, and it's really strong in those reactions, and so it really disrupts cellular metabolism. But other organisms have, also have adaptations, unlike humans in the case of lead, but they may have biochemical adaptations that make it possible for them to actually chelate the lead. Yeah. And that's where the bioremediation is coming in, right? Where Garcia has researched microorganisms that can bind with that lead and make it less bioactive. And that goes with a theme, not just the theme, but the title of the work, Bioremediating Cultures.
Yes.
Because of course you're seeing bioremediation in the ways that we've underscored.
Yeah.
But bioremediating a culture, like as in the human culture of consumerism, waste, and having the most vulnerable people in the culture pay the price for the consumer, for the production and the waste. And how do we remediate that?
The whole thing, right? On many different levels. Yeah.
Right.
Yeah.
And that's deeply ecological.
Yeah.
Right. In that way, that was the other thing that I was thinking about, is that extracting resources, the movement of resources and energy, that's essentially so deeply ecological and fundamentally about exchanges between organisms and their environment, right. Exactly as you were saying, with these objects.
Yeah.
And so I love that, like how not putting the art on a pedestal, inviting you to interact. Yeah. That's what she's talking about, the goal was too. Yeah. And so it's really, really cool.
And it's interesting
because you see that as an artist.
And you can't tell, she's showing a problem, a really bad problem affecting underprivileged, underrepresented groups, families, in a poisonous way. And so she's showing the problem, but she's also showing the solution. And you can't tell where one starts and where the other one ends. So right. There's actually which is the coolest thing about it, I think.
And involving the community in the solution.
Yeah.
Right, so working on a political level to create awareness and change on that level, but involving the community in the solution and getting a lot of people in the community signing up to be part of that. Yeah. Which really is so much about hope and agency.
Yeah. And that there is, and the technology is already there for a solution. If there was more political will, we could do things about a lot of this. But this is showing, hey, there's already a solution possible here.
There's so much chemistry in this story, and also in your knowledge and Garcia's use of the ceramic pieces.
They're also showing a way of taking the lead out of the soil, representing in that, and then I don't know, eggs are kind of like new life and all that sort of thing, if you want to go that direction. No, this is like really interacting with the problem, not representing the problem, it's interacting with the problem and changing the problem, which is really an incredible installation.
You just gave me chills because something that you as an artist just helped me see as a biologist. There's some biology that is why she called this vacuoles, right? And I somehow didn't get that on such a deep level as I did just now listening to you, where these are actually what she's inviting us to do is to be here corporeally inside of this plant cell, right, with these plant vacuoles, because this plant right here, in this plant's roots, it's actually taking up the bioactive, harmful lead out of the soil, chelating it, and then putting the chelated lead into its vacuoles, which are like membrane-bound pouches inside of the cell.
Well, it's so great because all these things, well, lead, we already talked about lead in a ceramic, used in ceramics for glazes, but also the chrome and the manganese and the irons and all these metals. It's just interesting because I think about them in terms of what do they do in terms of color and glazes and health-wise, and what fire do they burn out at, and what, et cetera, et cetera. There's also, you were talking about oxidation and reduction in terms of
physiology.
The physiology. There's also, when you fire ceramics, there's oxidation firings and reduction firings. And the oxidation is there's plenty of, it's like a giant toaster oven, or the fire has plenty of air to burn. So it's electric with the coils, or it has plenty of air to burn. Or reduction, you reduce oxygen in a fire that's at like 3,000 or 2,500 degrees or whatever you're firing to, and it's just starving for air. You starve it of air, and it starts robbing it from all the oxides in every single material in the clay and glaze, because they're all oxides.
Wow.
And it creates this sort of thermal chemical reaction for colors, different colors. So it's interesting to hear it, the physiological equivalent of, and functionality.
So what a trip for, I'm thinking of like, as a bio major, I took a year of Gen Chem. And so what a trip if when I'd been taking Gen Chem, I'd, like gotten to also take, say, ceramics. And like for ceramic students, if they're also in chemistry and learning about redox, and it's just like, because that makes, that it seems like would be really cool, because it would make the artists less afraid of science, because it's just like, I'm doing science. Right?
It's sneaky that way. Ceramics is sneaky.
And it would make the scientists like super, it's so fun to work with your hands. It's so fun to make things with your hands, and it would make the science less intimidating for the scientists too. Then you get to biochemistry, and that's where you realize why you had to learn about redox. Because all of these, all of these metabolic reactions that are happening inside of our cells all the time, it's all redox. And some of the most powerful ones, like photosynthesis or like oxygen exchange in our blood, have a heavy metal atom at the center of a big, of a big protein. And that heavy metal atom is, accepting and then giving off electrons.
Oh man, it's just mind blowing. I mean, there's the processes. So again, we're not talking about anything that's really static here, which is what's exciting. It's a very, she's representing, but also literally showing process, something that's alive and,